The nearest star to our Sun sits so close in cosmic terms that astronomers call it our stellar neighbour. But this neighbour hides a secret that rewrites everything you think you know about nearby space. Alpha Centauri is not one star. It is three. A gravitationally bound family containing a sun-like giant, an orange companion, and a violent red dwarf that happens to be the closest individual star to Earth. Scientists have confirmed planets orbiting this system, worlds that might harbour conditions for life just 4 light-years away. But the true scale of this triple star system, the distances between its components, the violence of its stellar activity, and the impossible challenge of ever reaching it, that is the story that will shatter your assumptions about cosmic proximity. If you enjoy journeys that transform how you see the universe, please like and subscribe. It helps more than you know. But for now, make yourself comfortable. Let's begin. Nearest neighbour. The phrase conjures images of friendly faces across a fence. Someone you could wave to from your porch. A house close enough to walk to in 30 seconds if you needed to borrow sugar. In human experience, nearest neighbour means accessible, reachable, close. Now consider your nearest stellar neighbour. Alpha Centauri sits so close to our solar system that astronomers literally call it next door. Scientific papers describe it as our cosmic backyard. Textbooks label it the closest star system to Earth. Every description emphasizes proximity, nearness. The comfortable suggestion that this neighboring sun exists just around the corner of our cosmic street. Here is the truth that shatters that illusion completely. If you launched humanity's fastest spacecraft toward Alpha Centauri today, your great-great-grandchildren would not see it arrive. Neither would their great-great-grandchildren. The journey would require nearly 7,000 years. When the spacecraft finally reached its destination, whatever civilization launched it would have risen, flourished, and crumbled into dust so thoroughly that no trace of its existence might remain. 7,000 years ago, humans had not yet invented writing. The pyramids did not exist. Bronze was a cutting-edge technology. The entirety of recorded human history, every empire that rose and fell, every war fought, every discovery made, every person who ever lived and died since we started keeping records, all of that fits inside the travel time to our nearest neighbour. This is the paradox that defines Alpha Centauri. Close enough that we can see it burning in the night sky. Close enough that we have confirmed planets orbit its stars. Close enough that we have identified worlds where liquid water might exist on surfaces bathed in alien sunlight. Yet so impossibly far that reaching it remains beyond any technology humanity currently possesses or can reasonably expect to develop within our lifetimes. The nearest star is not near at all, and understanding the true scale of this cosmic neighbour transforms everything you think you know about the universe and our place within it. The Parker Solar Probe holds the record for the fastest object humanity has ever created. This marvel of engineering swings close to the Sun, using our star's gravity to accelerate to velocities that defy human intuition. At its fastest, the Parker Solar Probe screams through space at approximately 430,000 miles per hour. Let that number sink in for a moment. 430,000 miles per hour. At that speed, you could circumnavigate the entire Earth in roughly 3.5 minutes. This represents the absolute pinnacle of human engineering applied to the problem of moving objects through the vacuum of space. Now, point this speed demon toward Alpha Centauri. At 430,000 miles per hour, the fastest velocity any human creation has ever achieved. The journey to our nearest stellar neighbour would require approximately 6,800 years. Call it nearly 7,000 years for the sake of comprehension. 7 millennia of continuous flight at speeds that would vaporize any conventional material if atmospheric friction existed in the interstellar void. The number crushes any casual optimism about cosmic travel. It reveals that our greatest technological achievements amount to essentially nothing when measured against interstellar distances. We have built machines that move faster than any natural object in the solar system except light itself. Those machines would need longer than recorded history to reach the star next door. Voyager 1 provides another crushing comparison. Launched in 1977, this spacecraft has travelled farther from Earth than any human-made object in history. For nearly 50 years, Voyager has been flying outward, crossing the boundary of the solar system and entering interstellar space. It currently sits approximately 15 billion miles from home, moving at roughly 38,000 miles per hour. At that pace, Voyager would require over 70,000 years to reach Alpha Centauri if it were heading in that direction. Which it is not. Modern humans might no longer exist as a species. The concept of the mission itself would have been forgotten, rediscovered, forgotten again, and perhaps rediscovered once more across dozens of civilizational cycles. This is what interstellar distances do to human ambition. They render our mightiest achievements cosmically trivial. The speeds that seem impossibly fast from a human perspective become laughably slow when applied to the gaps between stars. We have conquered planetary distances. We have sent robots to every major body in our solar system, yet the nearest star remains as inaccessible as it was when our ancestors first looked up and wondered what those points of light might be. The fundamental problem is not engineering. Engineers can build faster spacecraft given sufficient resources and motivation. The problem is physics itself. The distances involved are so vast that even revolutionary propulsion technologies would require decades or centuries to cross them. The speed of light imposes an absolute limit that no material object can exceed. And even light, the fastest thing in the universe, requires years to traverse the gap to Alpha Centauri. Light travels at 186,000 miles per second. Not per hour, per second. In the time it takes you to blink, light has crossed a distance roughly equal to 7 trips around Earth. In 1 second, a beam of light could circumnavigate our planet 7 times with distance to spare. This represents the cosmic speed limit, the absolute maximum velocity that physics permits for anything carrying information or mass through space. At this impossible speed, light still requires 4 years and 4 months to reach Alpha Centauri. Think about what that means. The fastest possible signal, the quickest conceivable message, the most urgent communication humanity could ever send, would take over 4 years to arrive at our nearest stellar neighbour. Einstein proved that nothing can travel faster. No warp drives, no wormholes, no science fiction shortcuts have ever been demonstrated to exist in actual physics. Light speed is the wall, and even light finds Alpha Centauri distant. Converting this travel time to distance produces numbers that stop meaning anything to human intuition. Alpha Centauri lies approximately 4.37 light-years from Earth. 1 light-year equals roughly 6 trillion miles. Multiply that out, and you get approximately 25 trillion miles separating us from the nearest star. 25 trillion miles. Written out fully, that number contains 13 digits. 25 followed by 12 zeros. If you tried to count to 25 trillion at 1 number per second, you would need nearly 800,000 years. The number itself resists comprehension. Human brains evolved to understand quantities relevant to survival on African savannas, counting members of your tribe, tracking prey across distances measured in miles, remembering locations of water sources and fruit trees across perhaps a few hundred square miles of territory. Nothing in our evolutionary history prepared us to grasp trillions of anything. Those 25 trillion miles contain almost nothing. The interstellar medium, as scientists call the space between stars, consists of approximately 1 atom per cubic centimetre. For comparison, the air you breathe contains roughly 25 quintillion molecules per cubic centimetre. The void between Earth and Alpha Centauri makes the best laboratory vacuum on our planet look positively crowded. This emptiness stretches for 25 trillion miles in every direction between here and there. cold beyond any temperature humans have experienced, dark beyond any night we can imagine, empty beyond any desert or ocean or void we have ever known. Just vacuum, punctuated by occasional hydrogen atoms drifting through the infinite dark. And this is the short trip. This is the nearest destination. This is what astronomers mean when they say Alpha Centauri is close. Scale comparisons help make these abstract numbers feel real. They translate cosmic distances into terms that human brains can process, even if the conclusions remain disturbing. Start with the Sun. Our star measures approximately 865,000 miles in diameter. Massive beyond comprehension from a human perspective. You could fit over 1 million Earths inside the Sun with room to spare. Now, shrink that enormous stellar furnace down to the size of a basketball, roughly 9.5 inches across. At this scale, Earth becomes a tiny grain of sand, about 2 millimeters in diameter. The Moon shrinks to a speck of dust, orbiting less than an inch from Earth's grain. The entire inner solar system, from Mercury to Mars, fits comfortably within a large room. Jupiter becomes a marble rolling around at the far end of a football field. Pluto, at its average distance, orbits somewhere around a mile away from your basketball sun. Now ask where Alpha Centauri sits in this model. The answer breaks the analogy entirely. Alpha Centauri, scaled to match your basketball sun, would be another basketball located approximately 4,400 miles away, roughly the distance from New York City to Berlin. Your entire desktop solar system model requires the Atlantic Ocean just to include the nearest star. Try another comparison. Imagine Earth as a single grain of sand, about 1 millimeter in diameter. At this scale, the Moon sits a few centimeters away. The Sun grows to the size of a beach ball 100 meters distant. The orbit of Pluto extends roughly 4 kilometers from your grain of sand Earth. Alpha Centauri. At this scale, the nearest star system lies approximately 3,200 kilometers away. A grain of sand in New York would have its nearest stellar neighbor somewhere past Bermuda, out in the mid-Atlantic Ocean. Even shrinking Earth to something you could lose between your fingertips does nothing to make the nearest star feel close. Or consider walking. Human beings move across the ground at roughly 3 miles per hour when walking purposefully. This pace carried our ancestors across continents over thousands of years. At 3 miles per hour, you could walk from New York to Los Angeles in approximately 5 months of continuous movement. At the same pace, walking to Alpha Centauri would require over 500 billion years. The universe itself is only 13.8 billion years old. You would need to walk for roughly 36 times the current age of the cosmos to reach the nearest star. Cars do not help much. Driving at 60 miles per hour, a reasonable highway speed, you could cross the continental United States in a couple of days. Driving to the Moon would take about 5 months. Driving to the Sun, ignoring the obvious problems with heat and lack of roads, would require roughly 175 years. Driving to Alpha Centauri would take approximately 47 million years. When you arrived, the continents on Earth would have drifted into unrecognizable configurations. Species that do not yet exist would have evolved, flourished, and gone extinct countless times. The human race would be a distant memory, if any memory at all remained. Commercial airplanes cruise at around 500 miles per hour. At that speed, you can fly from New York to London in about 7 hours. Pleasant, manageable, the kind of duration that fits within human experience. Flying to Alpha Centauri at commercial airplane speed would require approximately 5.7 million years. When you arrived, assuming your biological descendants somehow survived the journey, they would have evolved into something entirely different from human beings. 5 million years of evolution separates modern humans from our common ancestor with chimpanzees. The beings that arrived at Alpha Centauri would be as different from you as you are from the earliest hominids. Every analogy breaks down. Every comparison fails to capture the true scale. Human reference frames simply cannot accommodate interstellar distances. We evolved to understand walks across valleys and trips between villages. Our intuitions developed for a world where the longest journeys took months, where the farthest distances required generations to cross, where everything that mattered existed within a few hundred miles of home. The universe does not operate at human scales, and Alpha Centauri, the nearest star, demonstrates this with crushing finality. The cruel joke of Alpha Centauri is that we can see it so easily. Step outside on a clear night in the southern hemisphere or southern latitudes of the northern hemisphere. Look toward the constellation Centaurus. There it is, the third brightest star in the entire night sky, outshone only by Sirius and Canopus. A beacon so brilliant that ancient civilizations charted its position and incorporated it into their mythologies. You can see Alpha Centauri. You can watch it twinkle through atmospheric turbulence. You can photograph it with a camera mounted on a tripod. Children point at it and ask what it is. That specific collection of photons landing on your retina travelled for 4 years across 25 trillion miles of void to reach your eyes at this exact moment. Modern telescopes reveal extraordinary details about this nearby system. Spectrographs dissect the light, revealing chemical compositions and surface temperatures. Precise measurements track the positions of stars over decades, revealing orbital motions and gravitational relationships. Interferometers combine light from multiple telescopes to achieve angular resolution that distinguishes features within the system. We know that Alpha Centauri A resembles our Sun almost perfectly. We know that Alpha Centauri B burns slightly cooler and dimmer with an orange tint. We know that Proxima Centauri, the closest individual star to Earth, flickers with violent flares that dwarf anything our Sun produces. We have mapped their orbits, calculated their masses, estimated their ages, and modelled their evolutionary futures. We have even found planets. In 2016, astronomers confirmed an Earth-sized world orbiting Proxima Centauri in the habitable zone. A rocky planet where liquid water could potentially exist on the surface. The closest known exoplanet to Earth, sitting right there at our nearest stellar neighbour. Since then, additional planets have been discovered in the system, expanding our understanding of what worlds exist just next door. This knowledge tantalizes precisely because we cannot act on it. We have detected potentially habitable planets at the nearest possible stellar destination. We have identified exactly where life might exist beyond our solar system at the minimum possible distance. We have done everything except figure out how to actually go there. The situation resembles pressing your face against the window of a locked room. You can see everything inside with perfect clarity. You can describe the furniture, count the objects, analyze the decor, but you cannot enter. The glass remains impenetrable. The door stays locked. All your knowledge about the room's contents does nothing to get you inside. Alpha Centauri is that room. We have our faces pressed against the cosmic window, cataloguing everything we can observe, knowing that we cannot visit with any technology we currently possess. The planets orbit their stars, the stars orbit each other. Whatever processes unfold on those distant worlds continue without any possibility of human witness or intervention. We know where to go, we just cannot get there. Alpha Centauri qualifies as our nearest stellar neighbour because literally nothing exists closer. Survey the entire Milky Way galaxy, all 400 billion stars scattered across 100,000 light-years of space, and you will not find a single star system closer to our Sun than Alpha Centauri. This fact requires careful contemplation. 400 billion stars. A number so large that counting them at 1 per second would require 12,700 years. Scattered across a galaxy so vast that light itself needs 100 millennia to cross from edge to edge. And among all those countless stellar furnaces distributed across unimaginable volumes of space, the absolute closest one to us requires nearly 7,000 years to reach with our fastest spacecraft. The next nearest stars lie even farther away. Barnard's star, a dim red dwarf, sits approximately 6 light-years distant. Wolf 359, another red dwarf, famous for its appearance in science fiction, lies 7.8 light-years from Earth. Lalande 21,185 hovers at 8.3 light-years. Each successive neighbour increases the travel time by thousands of additional years. If Alpha Centauri proves inaccessible, these more distant stars remain exponentially more so. The few stars within 10 light-years of Earth represent our only plausible interstellar destinations within any conceivable technological framework. Beyond that modest sphere lies a galaxy of 400 billion stars that might as well exist in a different universe entirely. This isolation represents a fundamental feature of cosmic architecture. Stars are far apart, not somewhat far, not inconveniently far. Stars are separated by distances so enormous that travelling between them requires either accepting multimillennial journey times or developing technologies that currently exist only in theoretical physics. The average distance between stars in our region of the galaxy measures roughly 4 light-years. Alpha Centauri happens to be slightly closer than average, a lucky coincidence that makes it our nearest neighbour. But even this below-average stellar distance translates to trillions of miles of empty vacuum. The loneliness of star systems extends throughout the cosmos. Every stellar family floats in isolation, separated from its neighbours by gulfs that light itself takes years to cross. If intelligent beings exist on planets orbiting distant stars, they face the same brutal physics we do. The speed of light limits everyone equally. The vast spaces between stars isolate everyone equally. The universe appears designed to keep star systems apart, and Alpha Centauri, sitting at the minimum possible interstellar distance, demonstrates that even the shortest gap remains effectively unbridgeable with current technology. The light you see from Alpha Centauri tonight left that system 4 years ago. This simple fact creates one of the strangest aspects of cosmic observation. We never see any distant object as it currently exists. We only see the past, preserved in light that has been travelling toward us across the intervening space. When you look at Alpha Centauri, you are looking backward in time by 4 years. The photons striking your retina departed their source when events on Earth 4 years ago were unfolding. News that seemed urgent then has been forgotten. People who were alive then have died. Children who did not exist then have been born and taken their first steps. Alpha Centauri exists in a different present than we do. If something catastrophic happened there today, we would not know for 4 years. The light carrying that information is currently crossing the interstellar void at 186,000 miles per second and still has over 25 trillion miles to travel before reaching Earth. Whatever happens at Alpha Centauri in this moment remains hidden from us for years to come. Communication would face the same delay. If humanity somehow sent a message to Alpha Centauri today, using radio waves travelling at light speed, that message would arrive 4 years and 4 months later. Any response, sent immediately upon receipt, would take another 4 years and 4 months to return. An 8-year round trip represents the absolute minimum for any exchange of information. Real-time interaction is physically impossible. No conversation, no immediate feedback, no exchange that resembles anything like human dialogue. Communication with Alpha Centauri would require patience measured in years, with each side waiting nearly a decade to know whether their message was received and how the recipient responded. This temporal separation applies to everything we observe in the universe. The moon appears as it was 1.3 seconds ago. The sun appears as it was 8 minutes ago. Jupiter appears as it was between 35 and 52 minutes ago, depending on orbital positions. As distances increase, the time lag extends. Proxima Centauri appears as it was 4.2 years ago. The Andromeda Galaxy appears as it was 2.5 million years ago. The most distant objects we can observe appear as they were billions of years in the past, showing us a universe that no longer exists in the form we can see. Even our nearest stellar neighbour lives in a different temporal reality than we do. The Alpha Centauri system we observe tonight has already experienced 4 years of history we know nothing about. Stars have rotated, planets have orbited, storms have raged, flares have erupted, all of it invisible to us until the light carrying that information completes its long journey across the void. The universe forbids simultaneity across cosmic distances. There is no shared present between Earth and Alpha Centauri. There is only the past we can observe, and the future we must wait to see. Despite these crushing distances and impossible timescales, humanity has learned extraordinary things about our nearest stellar neighbour. The telescopes we have built can extract astonishing detail from those ancient photons arriving after their 4-year journey. We have mapped Alpha Centauri with a precision that would have seemed magical to astronomers just a century ago, and what we have found defies simple expectations. That single bright point of light visible in the southern sky conceals a secret. Alpha Centauri is not one star. Look through even a modest telescope, and the truth reveals itself. What appears as a single point of brilliance separates into 2 distinct objects, 2 separate stellar furnaces burning in the darkness. But even this doubled revelation does not complete the picture. A 3rd star lurks at the edges of the system, invisible to naked eyes, so dim that it escaped detection for centuries after the bright pair was discovered. This 3rd member, called Proxima Centauri, sits slightly closer to Earth than either of its brilliant companions. The nearest individual star to our solar system turns out to be one that ancient astronomers never knew existed. 3 suns locked in gravitational embrace. 3 nuclear furnaces converting hydrogen into helium across timescales that dwarf human civilization. 3 stellar masses executing an orbital dance that has continued for billions of years and will continue for billions more. The architecture of this triple system spans distances that challenge comprehension all over again. The physics governing their interactions operates on scales utterly removed from everyday experience. Understanding what truly exists at our nearest stellar neighbour requires confronting these realities. The bright point of light contains multitudes, and those multitudes dance through space according to rhythms that make human lifespans seem like the flutter of a mayfly's wing. For thousands of years, every human who gazed upon Alpha Centauri saw exactly one star. Ancient shepherds tracking its motion across the seasons saw one star. Greek philosophers cataloguing the heavens saw one star. Medieval astronomers charting constellations for navigation saw one star. Generation after generation, century after century, that brilliant point of light appeared singular and simple. They were all wrong. In 1689, a French Jesuit priest named Jean Richaud was tracking a comet from his observation post in Puducherry, India. The comet passed near that familiar bright star in the southern sky, and Richaud trained his telescope on the region to follow its path. What he saw through the eyepiece changed astronomical understanding forever. Alpha Centauri was not one star. It was 2. 2 distinct points of light appeared where generations had seen only one. 2 separate stellar furnaces burned in the darkness, close enough together that naked human eyes could not distinguish them, but clearly separate when magnified through even a modest telescope. Richaud had accidentally discovered only the 3rd binary star system ever identified by astronomers. Mizar in Ursa Major and Acrux in the Southern Cross had revealed their double nature earlier in the 17th century. Now, Alpha Centauri joined their ranks as a gravitationally bound pair, masquerading as a single point of brilliance. But even this revelation proved incomplete. 2 centuries would pass before astronomers discovered that the Alpha Centauri system harboured yet another secret. A 3rd star lurked at the edges, so dim that it escaped detection despite systematic surveys of the southern sky. This invisible companion would turn out to be the closest individual star to our solar system, hiding in plain sight while its brilliant siblings attracted all the attention. 3 suns, 3 nuclear furnaces converting hydrogen into helium through processes that release enormous energy. 3 gravitationally bound objects executing an orbital dance that has continued for nearly 5 billion years. all of it concealed within what appeared to be a single twinkling point in the constellation Centaurus. The history of Alpha Centauri's discovery reveals how gradually humanity uncovered the complexity hiding in our nearest stellar neighbour. Ancient astronomers knew the star well. Ptolemy catalogued it around 150 AD in his astronomical treatise, recording its position and brightness without any suspicion of its true nature. To Ptolemy and his contemporaries, stars were simply points of light fixed to a celestial sphere surrounding Earth. The idea that a single point might contain multiple objects would have seemed absurd. Arabic astronomers gave it the name that evolved into modern usage. They called it Rigel al-Quinturus, meaning the foot of the centaur, because it marks the right front hoof of the constellation figure. This name was Latinized and shortened over centuries, eventually becoming the Alpha Centauri we use today. Throughout this linguistic evolution, nobody suspected the star harboured secrets. Jean Rochot's 1689 discovery opened the first door to understanding. His observation of the binary pair proved that stars could exist in gravitationally bound systems, orbiting common centres of mass across astronomical distances. This realization transformed how scientists thought about stellar objects. Stars were not simply scattered randomly through space. They could form families, partnerships, even complex multi-body systems. But determining how far away this binary pair actually sat from Earth required another century and a half of technological advancement. Thomas Henderson tackled this problem in 1832 from the Royal Observatory at the Cape of Good Hope in South Africa. Henderson spent months making exacting positional measurements of Alpha Centauri, tracking tiny shifts in its apparent position as Earth moved from one side of its orbit around the Sun to the other. This technique, called stellar parallax, works like holding your thumb up and closing one eye, then the other. Your thumb appears to shift position against the background because your two eyes view it from slightly different angles. Similarly, a nearby star appears to shift position against more distant background stars when viewed from opposite sides of Earth's orbit, 6 months apart. The shift Henderson measured was incredibly small. Alpha Centauri moved back and forth by less than 1 arc-second against the stellar background. 1 arc-second equals 1/3600th of a degree, roughly the apparent width of a human hair viewed from 10 meters away. Detecting such minuscule motion required precision that pushed the limits of 19th century instrumentation. Henderson calculated the distance implied by his measurements and hesitated. The numbers seemed too remarkable to be true. His parallax angle suggested that Alpha Centauri lay closer to Earth than any other star, the nearest stellar neighbour in the entire sky. Publishing such an extraordinary claim risked professional embarrassment if the measurements proved wrong. So Henderson waited. He refined his calculations. He second-guessed his instruments. He delayed publication year after year, while doubt gnawed at his confidence. In 1838, German astronomer Friedrich Wilhelm Bessel announced successful parallax measurements for the star 61 Cygni. Bessel's publication proved that stellar parallax could be measured and that stars lay at distances of several light-years from Earth. Henderson finally felt confident enough to release his own results. He published his Alpha Centauri parallax in 1839, revealing what his measurements had shown years earlier. Alpha Centauri was indeed the closest star system to Earth, lying approximately 4.3 light-years away. Henderson had held the answer to one of astronomy's oldest questions and had almost let someone else claim the discovery through excessive caution. The final piece of the puzzle fell into place in 1915, when Robert Innes was working at the Union Observatory in Johannesburg, South Africa. Innes noticed a dim red star moving through space in an unusual way. Its direction and speed matched the motion of the Alpha Centauri binary pair almost exactly. Such coincidental motion seemed astronomically unlikely, unless this faint star was physically associated with the brighter system. Innes proposed that the red dwarf was gravitationally bound to Alpha Centauri A and B, orbiting the pair at an enormous distance. Further calculations revealed something extraordinary. This dim red dwarf actually sat slightly closer to Earth than either of its brilliant companions. Innes named it Proxima Centauri, from the Latin word meaning nearest, because he had discovered the closest individual star to our solar system. Humanity had finally mapped our nearest stellar neighbour in full. 3 stars, where ancient astronomers saw one. Complexity, where simplicity had been assumed. A triple system bound by gravity and executing orbital choreography on timescales that dwarf human existence. Alpha Centauri A dominates the system in size, mass, and luminosity. This stellar giant resembles our own Sun more closely than almost any other nearby star, making it a comforting presence in an otherwise alien cosmic neighborhood. Astronomers classify Alpha Centauri A as a G-type main sequence star, specifically spectral class G2. Our Sun carries the same classification. This means both stars share similar surface temperatures, similar chemical compositions, and similar internal processes of nuclear fusion, converting hydrogen into helium. The resemblance extends to precise measurements. Alpha Centauri amasses approximately 1.1 times our Sun. It burns roughly 50% brighter, radiating 1.5 times the solar luminosity. Its surface temperature hovers around 5,750 Kelvin, giving it the familiar yellowish-white appearance we associate with our own star. The physical dimensions match closely as well. Alpha Centauri spans approximately 1.2 solar diameters, roughly 865,000 miles across. You could fit over 1 million Earths inside this stellar sphere with room to spare. Like our Sun, it is a ball of hydrogen and helium plasma, so hot and dense at its core that atomic nuclei fuse together, releasing energy that eventually radiates outward as light and heat. The age of Alpha Centauri A falls within a few 100 million years of our Sun's age, approximately 4.85 billion years old. Both stars formed from the same galactic environment during the same general cosmic era. If you could somehow transport Earth to orbit Alpha Centauri A at the same distance we currently orbit the Sun, conditions would feel remarkably familiar. Days would be somewhat brighter. Due to the higher stellar luminosity, the slightly larger stellar disk would appear about 10% wider in the sky. But the basic experience of sunlight warming your face, of blue skies and golden sunsets, would remain recognizable. This familiarity makes Alpha Centauri a precious in astronomical terms. Among the hundreds of billions of stars in our galaxy, very few resemble our Sun as closely. Finding one just 4 light-years away represents extraordinary luck. Whatever conditions allowed life to develop around our particular stellar furnace might also exist around this nearly identical twin. The scientific designation Rigil Centaurus sometimes appears in star catalogues, derived from the original Arabic name meaning foot of the centaur, but most astronomers simply call it Alpha Centauri A, the brighter and larger component of our nearest stellar system. Alpha Centauri B provides contrast to its brilliant sibling. This second star burns cooler, smaller, and dimmer than either Alpha Centauri A or our own Sun, yet remains a fully functional stellar furnace capable of warming planets and driving complex chemistry. Astronomers classify Alpha Centauri B as spectral type K1, a category representing orange dwarf stars slightly smaller than yellow dwarfs like our Sun. The classification indicates immediately that this star differs from its companion in fundamental ways. Alpha Centauri B masses approximately 90% of our Sun, noticeably less than its larger companion. This reduced mass means lower core pressure and temperature, which translates to slower nuclear fusion rates and less energy output. The star radiates roughly half the luminosity of our Sun, considerably dimmer than Alpha Centauri. The surface temperature runs cooler as well, approximately 5,260 Kelvin compared to Alpha Centauri A's 5,750 Kelvin. This 500-degree difference might seem modest, but it fundamentally changes the quality of light the star produces. Alpha Centauri b glows with a distinctly orange tint compared to the yellowish white of its companion. The cooler surface emits more light at longer wavelengths, shifting the color toward the red end of the spectrum. Standing on a hypothetical planet orbiting Alpha Centauri b, you would notice sunlight that appeared warmer and more golden than Earth's sunshine. Shadows would carry subtle orange undertones. The entire visual environment would feel slightly alien, despite the star's overall similarity to our Sun. The name Ptolemy sometimes appears in references to this star, derived from Arabic astronomical traditions. Like its companion's designation Rigil Centaurus, this name has largely fallen out of common use in favour of the systematic Alpha Centauri b. Despite being smaller and cooler than our Sun, Alpha Centauri b remains perfectly capable of hosting planetary systems. Its habitable zone, the region where liquid water could exist on a planetary surface, lies closer to the star than Earth's distance from the Sun. Any world orbiting in that zone would receive comparable warmth, despite the lower stellar luminosity. The combination of Alpha Centauri A and B creates interesting possibilities for any observer within the system. From a planet orbiting either star, the companion would appear as the brightest object in the night sky aside from any local moons. The interplay of light from two different coloured stars would create illumination conditions unlike anything we experience on Earth. Proxima Centauri completes the triple system with characteristics utterly different from its brilliant companions. This tiny red dwarf star represents the smallest category of objects capable of sustaining hydrogen fusion in their cores. Astronomers classify Proxima as spectral type M5, deep within the red dwarf category. These stars occupy the bottom of the stellar mass scale. Any smaller, and the object would lack sufficient core pressure to ignite nuclear fusion, becoming a brown dwarf or failed star instead. Proxima masses only 12.5% as much as our Sun. If you gathered 8 Proximas together, their combined mass would still fall short of one solar mass. This remarkable lightness explains the star's other extreme characteristics. The luminosity of Proxima Centauri shocks anyone accustomed to thinking about stars as brilliant objects. This star radiates approximately 1.5 thousandths of our Sun's energy output. You would need to combine the light from roughly 650 Proximas to equal the output of one Sun. You would need over 1,000 Proximas to match Alpha Centauri A. The physical dimensions reflect this meagre output. Proxima spans only 14% of the Sun's diameter, roughly 107,000 miles across. This makes it only about 20% larger than Jupiter, the largest planet in our solar system. If you could place Proxima and Jupiter side by side, the star would appear barely larger than the gas giant. The surface temperature hovers around 3,000 Kelvin, less than half the temperature of our Sun's photosphere. This relatively cool surface gives Proxima its deep red colour, so different from the brilliant whites and yellows of larger stars. Much of the energy Proxima radiates emerges in infrared wavelengths invisible to human eyes. The visible light it produces appears distinctly reddish, creating an alien illumination environment unlike anything in human experience. Yet Proxima Centauri harbours a secret that its dim appearance conceals. This tiny star is extraordinarily violent. Red dwarfs generate intense magnetic fields through convective processes that churn their entire stellar interiors. Unlike our Sun, which is convective only in its outer layers, Proxima churns from core to surface. This constant overturning generates magnetic activity across roughly 88% of the stellar surface. These magnetic fields periodically release tremendous energy through stellar flares. Proxima flares regularly, sometimes increasing its brightness by enormous factors within seconds. The violence of these eruptions far exceeds anything our relatively calm Sun produces. Despite its diminutive size and violent temperament, Proxima Centauri holds a unique distinction. It is the closest individual star to our solar system, sitting slightly closer to Earth than either of its brilliant companions. The nearest star turns out to be one so dim that human eyes cannot detect it without telescopic assistance. Robert Innes discovered this hidden neighbour only in 1915, more than 2 centuries after Reshape identified the bright binary pair. Proxima had been there all along, slowly circling its distant companions, waiting for someone to notice its telltale motion through the cosmos. The 2 bright stars of Alpha Centauri execute an orbital dance that has continued for billions of years. Alpha Centauri A and B circle their common centre of mass in a period of approximately 79.9 years. In human terms, this means a single orbit takes most of an adult lifetime to complete. The orbital path traces a pronounced ellipse with eccentricity of 0.52. This high eccentricity means the distance between the 2 stars varies dramatically over the course of each orbit. At closest approach, called periastron, Alpha Centauri A and B pass within approximately 11 astronomical units of each other. 1 astronomical unit equals the distance from Earth to our Sun, roughly 93 million miles. 11 astronomical units matches the distance from our Sun to Saturn. At this point in their orbit, the 2 stars are close enough that their gravitational influence on each other becomes intense. At farthest separation, called a pastron, the 2 stars swing out to approximately 35 astronomical units apart. This matches the distance from our Sun to Pluto, near the edge of what we traditionally considered the solar system boundary. The stars are 3 times farther apart at a pastron than at periastron. This dramatic variation creates remarkable effects for any hypothetical observer within the system. Imagine standing on a planet orbiting Alpha Centauri A. At periastron, Alpha Centauri B would appear in your sky as a brilliant diamond, roughly 500 times brighter than Venus appears from Earth. The companion star would cast noticeable shadows, contribute measurable warmth, and dominate the night sky with brilliance that outshines everything except your own Sun. At a pastron, that same companion would have retreated to 3 times the distance. It would still appear as the brightest star in your sky, but merely as a brilliant point rather than an overwhelming presence. The dramatic variation would mark the passage of decades, a slow dance visible across a human lifetime. The gravitational interaction between these 2 stars affects the stability of any planetary orbits within the system. Computer simulations reveal that planets can exist in stable configurations around either star individually, but only within certain distance limits. Planets orbiting Alpha Centauri A must remain within approximately 3 astronomical units to avoid gravitational disruption from the companion star during close approaches. Planets around Alpha Centauri B face similar constraints. Beyond these limits, the gravitational perturbations from the companion star would gradually destabilize planetary orbits over millions of years. The planet might be ejected from the system entirely, or sent spiraling inward toward its host star. The binary configuration creates forbidden zones where stable orbits cannot exist. Fortunately, the habitable zones of both stars fall well within the stability limits. Rocky planets could theoretically exist in regions where liquid water might persist on their surfaces, orbiting either star without facing gravitational ejection from the binary companion. The 79-year orbital period spans most of a human lifetime, but represents the blink of an eye in cosmic terms. During the 4.85 billion years since the system formed, Alpha Centauri A and B have completed approximately 60 million orbits around each other. 60 million close approaches, 60 million recessions, an eternal waltz that will continue for billions of years to come. Proxima Centauri orbits the central binary pair at a distance that challenges comprehension even after grappling with the scales discussed earlier. This tiny red dwarf circles its brilliant companions at approximately 13,000 astronomical units, ranging from perhaps 4,300 astronomical units at closest approach to 13,000 at farthest. Converting to miles provides numbers that lose all human meaning. 13,000 astronomical units equals approximately 1.2 trillion miles. The distance separating Proxima from Alpha Centauri A and B exceeds the distance from Earth to the Sun by a factor of 13,000. Light itself requires over 2 months to travel from Proxima to the central binary at current separation. The fastest thing in the universe needs nearly 10 weeks to cross the gap within this single star system. The orbital period of Proxima around its distant companions spans approximately 550,000 years. Consider what this timescale means. When Proxima last completed an orbit and returned to its current position, anatomically modern humans did not exist. Our species emerged, developed language, invented agriculture, built civilizations, created writing, waged wars, launched spacecraft, and began contemplating interstellar travel, all within a single orbital period of this slowly circling red dwarf. During the 4.85 billion years since the Alpha Centauri system formed, Proxima has completed roughly 9,000 orbits around the binary pair. 9,000 circuits, each taking longer than human existence, accumulated over geological timescales. For decades after Innes discovered Proxima in 1915, astronomers debated whether this dim star was truly gravitationally bound to the Alpha Centauri system. The enormous distance separating Proxima from the bright pair made confirmation difficult. Perhaps Proxima was merely passing through the same region of space, a cosmic coincidence rather than a genuine family member. Modern observations have settled this question definitively. Precise measurements of Proxima's motion confirm that it is gravitationally bound to Alpha Centauri A and B. The 3 stars form a genuine triple system, with Proxima tracing a vast orbit around the central binary over hundreds of millennia. The hierarchical arrangement of this system provides stability. Proxima orbits so far from the central binary that it treats the AB pair effectively as a single massive object. The binaries' mutual orbit around their common centre of mass averages out from Proxima's distant perspective. This separation prevents the complex 3-body gravitational interactions that would otherwise destabilize the system over cosmic time. If Proxima orbited much closer to the binary pair, gravitational interactions between all 3 stars would eventually tear the system apart. The enormous gulf between Proxima and its companions allows each component to orbit relatively unperturbed by the others. Our Sun will die in approximately 5 billion years. The hydrogen fuel in its core will exhaust, and our star will swell into a red giant before shedding its outer layers and collapsing into a white dwarf. Alpha Centauri A faces a similar fate on a similar timescale. These sun-like stars burn bright but brief in cosmic terms. Proxima Centauri will outlast them by an almost incomprehensible margin. Red dwarf stars burn their hydrogen fuel so slowly that they will shine for trillions of years. Not billions, trillions. The numbers stretch beyond any meaningful reference frame. The current age of the universe is approximately 13.8 billion years. Everything that has ever happened, from the Big Bang through the formation of galaxies, stars and planets, through the emergence of life on Earth and the evolution of human consciousness, all of it fits within 13.8 billion years. Proxima Centauri will continue fusing hydrogen in its core for at least 4 trillion years. Possibly much longer. This means Proxima has consumed less than 0.5% of its total lifespan, despite already existing for 4.85 billion years. When our Sun dies, Proxima will still be burning. When every sun-like star in the current universe has exhausted its fuel, Proxima will still be burning. The red dwarf will continue shining for roughly 300 times longer than the current age of the universe. The implications for any planets orbiting Proxima are profound. Life on Earth has existed for roughly 4 billion years, during which our Sun has remained relatively stable. But life around Proxima would have essentially unlimited time to evolve. Trillions of years of stable stellar output. Time for evolutionary experiments that make Earth's biological history look like a brief afternoon. Red dwarfs like Proxima represent the true inheritors of cosmic time. The brilliant stars that dominate our night sky will all die relatively soon in astronomical terms. The dim red dwarfs that barely register to human eyes will outlast everything else, patiently burning through the long darkness of the far future. Comparing the Alpha Centauri system to our own solar system illuminates both similarities and profound differences in cosmic architecture. Our solar system extends from Mercury at approximately 0.4 astronomical units from the Sun to the distant reaches of the Oort cloud at perhaps 100,000 astronomical units. This gives our system a maximum radius comparable to the orbital distance of Proxima from the Alpha Centauri binary, but the distribution of mass differs dramatically. Our solar system concentrates virtually all its mass in a single central object. The Sun contains 99.86% of the entire system's mass. All the planets, moons, asteroids, comets, and scattered debris account for less than 1/5 of 1% of the total. The Sun dominates gravitationally, and everything else simply follows its rules. Alpha Centauri distributes its mass among 3 substantial stellar objects. Alpha Centauri A contributes 1.1 solar masses. Alpha Centauri B adds 0.9 solar masses. Proxima contributes another 12% of a solar mass. The total system mass approaches 2.1 times our Sun's mass, with significant gravitational contributions from multiple sources. This distributed mass creates gravitational complexity far beyond anything in our solar system. Planets orbiting Alpha Centauri must account for perturbations from Alpha Centauri B. Objects in the outer regions of the system feel gravitational influences from all 3 stellar masses. The orbital dynamics require sophisticated computer modeling to predict accurately. The presence of multiple stars also affects how planets might have formed in this system. The gravitational stirring from companion stars could have disrupted planet-forming disks, preventing material from accreting into large bodies. Alternatively, the complex gravitational environment might have concentrated material in certain regions, enhancing planet formation in some areas while suppressing it in others. For decades, astronomers wondered whether this triple system could harbour planets at all. The gravitational dance seemed potentially hostile to the delicate processes that create worlds. Yet, in 2016, everything changed. Astronomers announced the confirmed detection of an Earth-sized planet orbiting Proxima Centauri, a rocky world sitting in the habitable zone of the nearest star to Earth, the closest known exoplanet to our solar system, existing right there at our nearest stellar neighbour. Since that discovery, additional planets have been found in the Proxima system. The gravitationally complex environment that seemed hostile to planet formation had produced worlds after all, but the planets of Alpha Centauri face conditions unlike anything in our solar system. The violent flare activity of Proxima Centauri, the potential atmospheric stripping from high-energy radiation, the alien illumination from a red dwarf star that emits most of its energy in wavelengths human eyes cannot see. The worlds next door exist. The question that remains is whether anything could survive on them. On August 24, 2016, the European Southern Observatory held a press conference that changed humanity's understanding of our cosmic neighbourhood forever. After months of careful verification and peer review, astronomers announced they had confirmed the existence of a planet orbiting Proxima Centauri. Not just any planet, an Earth-sized world sitting squarely in the habitable zone of the nearest star to our solar system. The implications crashed through the scientific community like a shockwave. For decades, astronomers had wondered whether planets existed around Alpha Centauri. The complex gravitational dynamics of the triple system seemed potentially hostile to planetary formation. Many researchers assumed that even if planets had formed, the habitable zones around these stars would prove empty. They were wrong. Proxima Centauri b, as the new world was designated, orbits at a distance where liquid water could theoretically exist on its surface. The temperature conditions, given the right atmospheric composition, could permit oceans. The mass suggests a rocky composition similar to Earth, and this world sits just 4.2 light-years away, closer than any other known exoplanet. The press conference sparked immediate speculation about extraterrestrial life. If a potentially habitable world existed at the nearest possible stellar destination, surely this increased the chances that life had developed there. The universe seemed to be offering humanity a gift, placing a possibly Earth-like world at the closest conceivable location. But as scientists examined the data more closely, the optimism began to crack. The same observations that confirmed Proxima B's existence also revealed troubling details about its environment. The star it orbits, that tiny red dwarf discussed earlier, harbors violent secrets that challenge every assumption about habitability. The question that emerged from that 2016 announcement remains unanswered today. Could life actually survive on a world orbiting Proxima Centauri? The answer proves far more complicated than anyone initially hoped. Proxima Centauri b orbits its parent star at a distance that seems impossibly close by solar system standards. The planet circles Proxima at approximately 0.05 astronomical units from the stellar surface. For comparison, Mercury, the innermost planet in our solar system, orbits the Sun at roughly 0.4 astronomical units. Proxima b sits 8 times closer to its star than Mercury sits to ours. This extreme proximity produces an orbital period that defies terrestrial intuition. Proxima b completes one full circuit around its star every 11.2 Earth days. A year on this world lasts less than 2 weeks by our calendar. Birthdays would arrive with dizzying frequency. Seasons, if they exist at all, would cycle through in days rather than months. The detection method that revealed Proxima b relies on measuring tiny wobbles in the star's motion, caused by the planet's gravitational pull. As the planet orbits, it tugs on Proxima Centauri, causing the star to execute a small circular or elliptical motion around the common center of mass. Sensitive spectrographs can detect this stellar wobble through Doppler shifts in the star's light. The wobble reveals both the orbital period and the minimum mass of the unseen planet. For Proxima b, that minimum mass comes out to approximately 1.07 times Earth's mass. The planet is slightly heavier than our world, suggesting it likely has similar rocky composition and comparable surface gravity. The actual mass could be somewhat higher depending on the orbital inclination relative to our line of sight. If we view the orbit edge-on, we detect the full wobble and measure the true mass. If the orbit is tilted, we detect only a component of the motion and underestimate the planet's heft. Without transit observations showing the planet crossing its star's face, the true mass remains uncertain. But the minimum mass already tells us something profound. Proxima b is not a gas giant. It is not a Neptune-like ice world. It is a rocky planet comparable in size and mass to Earth, sitting in the habitable zone of the nearest star. The habitable zone represents one of the most important concepts in the search for life beyond Earth. Sometimes called the Goldilocks zone, this region around any star marks the distances where conditions are not too hot, not too cold, but just right for liquid water to exist on a planetary surface. The boundaries of the habitable zone depend entirely on the star's luminosity. Bright, hot stars have habitable zones far from their surfaces. Dim, cool stars have habitable zones tucked in close. The principle remains constant, but the specific distances vary enormously. Proxima Centauri's extreme dimness, radiating only about 1.5 thousandths of our Sun's energy output, places its habitable zone extraordinarily close to the stellar surface. Calculations suggest liquid water could potentially exist on planets orbiting between approximately 0.04 and 0.09 astronomical units from Proxima. At 0.05 astronomical units, Proxima b sits comfortably within this range. The planet receives approximately 65% of the energy that Earth receives from our Sun. This reduced irradiation might seem like it would produce a frozen world, but atmospheric greenhouse effects could easily compensate. Earth's atmosphere traps enough heat to raise our surface temperature by roughly 33 degrees Celsius above what bare rock would experience. A thicker atmosphere, or one with more potent greenhouse gases, could warm Proxima b to Earth-like temperatures. The equilibrium temperature, calculated assuming no atmosphere, comes out to approximately minus 39 degrees Celsius, or 234 Kelvin. Cold, certainly, but not impossibly so. Mars has a similar equilibrium temperature, yet shows evidence of liquid water in its past. With the right atmospheric composition, Proxima b could be temperate or even warm. The tantalizing possibility of Earth-like conditions on the nearest exoplanet sparked tremendous excitement in 2016, but that excitement soon collided with sobering physical realities. The extreme proximity of Proxima b to its star creates a phenomenon called tidal locking that would fundamentally alter any experience of this world. Tidal locking occurs when gravitational forces slow a body's rotation until one side permanently faces the object it orbits. The Moon demonstrates this effect perfectly, always showing the same face to Earth while its far side remains forever hidden from direct terrestrial view. Proxima b almost certainly experiences the same fate. The planet orbits so close to Proxima Centauri that tidal forces have had billions of years to drain rotational energy from its spin. Computer models suggest that tidal locking would occur within millions of years at Proxima b's orbital distance. Given the system's age of 4.85 billion years, the planet has been locked for essentially its entire existence. Tidal locking creates a world divided into eternal day and eternal night. One hemisphere permanently faces the star, bathed in constant ruddy illumination from the red dwarf's surface. The other hemisphere faces away, experiencing perpetual darkness without ever seeing its star rise above the horizon. There is no sunrise on a tidally locked world, no sunset, no day-night cycle. Just endless light on one side and endless dark on the other. The temperature implications are severe. The day side receives continuous stellar heating with no nighttime to radiate accumulated energy into space. Surface temperatures could climb to extremes that would vaporize any exposed water. The night side experiences the opposite problem. Without any stellar input, the dark hemisphere radiates heat away continuously. Temperatures could plunge far below anything experienced on Earth, potentially cold enough to freeze atmospheric gases into surface ice. This temperature gradient creates challenges for habitability that Earth never faces. On our world, the atmosphere and oceans redistribute heat from equator to poles, from day side to night side. Rotation ensures that every location experiences both heating and cooling phases. The result is a relatively moderate global temperature distribution. On tidally locked Proxima b, the temperature distribution could be catastrophically extreme. Some models suggest the day side could reach temperatures exceeding 100 degrees Celsius, while the night side plummets to minus 100 degrees Celsius or colder. The habitable region might be confined to a narrow band at the terminator, the boundary between eternal day and eternal night, where twilight conditions persist forever. This terminator zone could potentially support liquid water and moderate temperatures. The geometry of tidal locking means this twilight band extends completely around the planet, forming a ring-shaped habitable region. Any life that evolved on Proxima b might be confined to this narrow strip, living in perpetual sunset or sunrise. However, computer simulations suggest that sufficiently thick atmospheres could redistribute heat effectively enough to moderate these extremes. Atmospheric circulation, driven by the temperature differential between hemispheres, could transport warmth from day side to night side, preventing the most extreme temperature scenarios. A dense atmosphere might make large portions of the surface habitable, rather than just the terminator zone. There is also a possibility that Proxima b is not perfectly tidally locked. If the planet's orbit has significant eccentricity, exceeding roughly 0.1, it might have settled into a 3-to-2 spin-orbit resonance like Mercury in our solar system. In this configuration, the planet would rotate 3 times for every 2 orbits, creating a day-night cycle, albeit an extremely strange one by Earth standards. The tidal locking question remains unresolved without better observations, but even the most optimistic scenarios describe a world fundamentally alien to human experience. Eternal day, eternal night, or a bizarre rhythm where the sun traces complex patterns across the sky over weeks rather than hours. Whatever surface conditions Proxima b possesses, they bear no resemblance to Earth. The most serious challenge to habitability on Proxima b comes not from tidal locking but from the violent stellar environment. Proxima Centauri ranks among the most active flare stars known to astronomers. The violence it inflicts on any nearby planet may have rendered habitability impossible regardless of other favourable conditions. Red dwarf stars like Proxima generate intense magnetic fields through convective processes that churn their entire stellar interiors. The core and radiative zone remain relatively calm, but Proxima churns from core to surface, with roiling plasma carrying heat outward through the entire stellar volume. This full-body convection generates magnetic activity across the stellar surface. Researchers estimate that approximately 88% of Proxima's surface may be magnetically active at any given time. Compare this to our Sun, which shows magnetic activity across only a small percentage of its surface even during solar maximum. The magnetic fields periodically release stored energy through stellar flares. These eruptions occur when twisted magnetic field lines suddenly reconnect, converting magnetic energy into radiation and accelerated particles with explosive violence. Our Sun produces flares, but Proxima's flares dwarf solar events by orders of magnitude. On May 1, 2019, astronomers detected one of the most powerful stellar flares ever recorded from any star. Proxima Centauri erupted with a superflare that momentarily transformed this dim red dwarf into something terrifying. The flare increased Proxima's brightness by a factor of roughly 1,000 in millimeter radio wavelengths. In far ultraviolet light, the brightening reached a factor of 14,000. For a few seconds, Proxima radiated 14,000 times more ultraviolet energy than its normal quiescent output. This superflare lasted only seconds, but the energy release was catastrophic by any planetary standard. The radiation burst that struck Proxima b during those seconds exceeded anything Earth has experienced from our relatively calm Sun by enormous margins. And this was not a rare event. Proxima flares regularly. Smaller eruptions occur frequently, with major flares happening multiple times per year. The 2019 superflare was exceptional in its intensity, but the overall pattern of violent stellar activity is normal for this star. Proxima has been assaulting any nearby planets with radiation bursts for billions of years. The implications for Proxima b are severe. Under normal conditions, Proxima b receives approximately 30 times more extreme ultraviolet radiation than Earth receives from our Sun. The planet also receives roughly 250 times more X-rays than Earth. These forms of high-energy radiation damage biological molecules, ionize atmospheric gases, and drive chemical reactions that could destroy organic compounds. During major flares, the radiation bombardment increases by additional orders of magnitude. The 2019 superflare would have blasted Proxima b with thousands of times its normal extreme ultraviolet dose. Any organism exposed on the surface during such an event would have received lethal radiation within seconds, but the immediate radiation damage may be less significant than the long-term atmospheric effects. High-energy ultraviolet photons and X-rays ionize atmospheric gases, stripping electrons from atoms and molecules. These ionized particles become vulnerable to the stellar wind, a continuous outflow of charged particles from the star's corona. The stellar wind can sweep ionized atmospheric gases away from a planet, gradually eroding its protective envelope into space. Proxima Centauri's stellar wind is more intense than our Sun's. Combined with the frequent flare activity that continuously ionizes atmospheric gases, the erosion rate on Proxima b could be devastating. Some researchers have calculated atmospheric loss rates for Proxima b based on observed stellar activity. The conclusions are grim. One Harvard-Smithsonian analysis suggested that atmospheric stripping rates could be so high that habitability is implausible. Over 4.85 billion years of continuous bombardment, any primordial atmosphere Proxima b possessed may have been completely removed. The cruel irony cuts deep. Proxima b sits in the habitable zone, at the right distance for liquid water to exist. but the stellar environment may have stripped away the very atmosphere needed to maintain that water in liquid form. The planet occupies the Goldilocks zone of a star that makes habitability nearly impossible through other mechanisms entirely. Despite the grim prognosis from stellar activity, the question of whether life could survive on Proxima b remains genuinely open. Scientists have proposed various scenarios under which the planet might retain habitability despite the challenging conditions. The case against life on Proxima b rests on multiple pillars. Billions of years of flare bombardment would have repeatedly sterilized any exposed surface. Atmospheric stripping would have removed protective gases that shield against radiation and maintain surface pressure for liquid water. Tidal locking creates extreme temperature gradients that confine potentially habitable regions to narrow zones. Surface radiation levels during flare events would exceed lethal doses for any known Earth organism. Each argument carries substantial weight. Together, they paint a picture of a world that may be rocky, Earth-sized, and technically in the habitable zone, but ultimately hostile to life as we understand it. Yet counter-arguments exist for each objection. A strong planetary magnetic field could deflect charged particles from the stellar wind, dramatically reducing atmospheric erosion rates. Earth's magnetic field performs exactly this function, protecting our atmosphere from solar wind stripping. If Proxima b possesses a similar magnetic dynamo, powered by a liquid iron core, atmospheric loss rates might be manageable. Volcanic outgassing could replenish atmospheric gases faster than stellar wind strips them away. Earth continuously releases gases from its interior through volcanic activity. A geologically active Proxima b could maintain an atmosphere through constant resupply, even under significant erosion pressure. The planet's initial volatile inventory might have been enormous. Worlds that form in the outer regions of planetary systems and migrate inward often carry vast quantities of water and other volatiles. If Proxima b formed with an ocean dozens of times Earth's volume, even billions of years of erosion might not deplete it entirely. A sufficiently thick atmosphere would protect the surface from radiation even during major flares. Earth's atmosphere absorbs most incoming ultraviolet radiation before it reaches the surface. An atmosphere several times denser than Earth's could provide even more effective shielding. Ocean depths would offer radiation protection regardless of atmospheric conditions. Any organisms living more than a few meters below the surface of a Proxima b ocean would be shielded from stellar flares entirely. Life could exist in subsurface environments completely isolated from surface conditions. Earth hosts extensive microbial ecosystems in deep rock formations, accessing chemical energy rather than sunlight. Similar life forms on Proxima b could thrive beneath the surface, indifferent to stellar flares above, and Earth's extremophile organisms demonstrate remarkable radiation tolerance. Deinococcus radiodurans, a bacterium found in terrestrial environments, can survive radiation doses thousands of times higher than lethal human exposure. Life finds ways to adapt to seemingly impossible conditions. One particularly intriguing hypothesis proposes that Proxima b might be a habitable evaporated core. In this scenario, the planet originally formed with a massive hydrogen envelope. Similar to a mini Neptune, this primordial atmosphere shielded the rocky core and any surface water from the young star's most intense activity. Proxima Centauri, like all red dwarfs, was more active in its youth than it is today. The early bombardment would have been even more severe than current conditions. A thick hydrogen envelope could have protected the planet through this dangerous phase. Over billions of years, the hydrogen envelope would have been gradually stripped away by stellar activity. But by the time the envelope disappeared, the star had calmed somewhat, and the underlying rocky planet might have retained significant water and atmospheric gases. This hypothesis remains speculative. No confirmed atmosphere has been detected around Proxima b despite multiple observation attempts. The question of whether any protective envelope exists remains unanswered. The honest assessment is that habitability on Proxima b could go either way. The conditions are challenging but not necessarily prohibitive. Life might exist there, perhaps in forms adapted to radiation and extreme conditions. or the planet might be a sterile rock, scoured clean by billions of years of stellar violence. Only direct observation can resolve the question. Proxima Centauri hosts more than one confirmed planet. The system contains at least 2 worlds, possibly 3, each occupying different regions around the violent red dwarf. Proxima Centauri d was confirmed in 2022, adding another member to our nearest planetary system. This world orbits even closer to the star than Proxima b, sitting at approximately 0.03 astronomical units from the stellar surface. At this extreme proximity, Proxima d completes an orbit every 5.1 days. A year on this innermost world lasts less than a week. The planet whips around its star so rapidly that its orbital velocity exceeds anything in our solar system. The mass of Proxima d measures approximately 1/4 of Earth's mass, making it one of the lightest exoplanets ever discovered. This tiny world probably resembles a scaled-up version of Mars more than Earth. A small rocky body without sufficient gravity to retain a substantial atmosphere. Proxima d lies well inside the habitable zone, far too close to its star for liquid water to exist on its surface. Whatever conditions prevail there, habitability is not among them. The planet receives such intense stellar radiation that any water would have been vaporized and lost to space long ago. The significance of Proxima d lies not in its habitability potential, but in what it reveals about planetary formation in this system. The presence of multiple rocky planets suggests that the conditions around Proxima Centauri allowed solid worlds to form and survive, despite the complex gravitational environment and violent stellar activity. A third planet, Proxima Centauri c, has been proposed but remains controversial. If it exists, this world would be substantially larger than either of its confirmed siblings. The proposed mass of Proxima c approaches 7 Earth masses, placing it in the category of mini-Neptunes or super-Earths. At this size, the planet might possess a thick gaseous envelope rather than a purely rocky surface. Proxima c would orbit at approximately 1.5 astronomical units from its star, far outside the habitable zone. At this distance, temperatures would plummet to Neptune-like levels. Any atmosphere would likely be composed of hydrogen, helium, and various ices rather than nitrogen and oxygen. The orbital period of roughly 5 years makes Proxima c difficult to detect. The stellar wobble it induces takes years to complete a full cycle, requiring long observational campaigns to confirm. Different research groups have reported conflicting results about whether the signal is genuine or an artifact of stellar activity mimicking a planetary signature. Additional planets may exist in the Proxima system awaiting discovery. The detection methods astronomers use have inherent blind spots. Planets with certain orbital orientations or masses might escape detection entirely. The 3 known or suspected worlds likely represent only a partial census of whatever planetary family Proxima Centauri actually hosts. The bright stars Alpha Centauri A and B present different challenges for planet hunters. The radial velocity method that detected Proxima b works by measuring tiny Doppler shifts in starlight. But Alpha Centauri A and B are active stars with surface phenomena that produce their own spectral variations. Distinguishing a planetary wobble from stellar noise requires extreme precision and long observation campaigns. In 2021, astronomers announced a candidate planet around Alpha Centauri, detected through direct imaging. This technique photographs the actual light reflected or emitted by a planet, rather than inferring its presence from stellar wobbles. The candidate object, if real, would orbit in the habitable zone of the Sun-like star. An Earth-like world around Alpha Centauri A would face far more benign conditions than anything orbiting Proxima. The larger star is far less active, producing minimal flares and much lower levels of damaging radiation. However, subsequent analysis raised questions about whether the detected signal represented an actual planet or an instrumental artifact. The extraordinary difficulty of direct imaging around bright nearby stars makes false positives a constant concern. The Alpha Centauri A candidate remains unconfirmed. as of current observations, computer simulations provide guidance about where stable planetary orbits could exist in the binary system. Despite the gravitational complexity of two stars orbiting each other, significant stable zones exist around each component. Planets orbiting Alpha Centauri A could remain stable within approximately 3 astronomical units of that star. This encompasses the entire habitable zone, meaning Earth-like worlds could theoretically exist there without being gravitationally disrupted by Alpha Centauri B. Similarly, planets around Alpha Centauri B could maintain stable orbits within roughly 2.5 astronomical units. The habitable zone of this cooler star lies closer in, well within the stability limit. Rocky worlds with liquid water could orbit there indefinitely. The fact that stable habitable zones exist around both bright stars keeps hopes alive that Earth-like planets might be found there. Future missions with improved detection capabilities may finally answer whether our nearest stellar neighbours host worlds where life could thrive without the challenges that plague Proxima b. The proximity of the Alpha Centauri system makes it the most important target for atmospheric characterization of exoplanets. At 4 light-years distance, any planets there can be studied in far greater detail than worlds around more distant stars. The James Webb Space Telescope possesses capabilities for analyzing exoplanet atmospheres through spectroscopy. When a planet transits across its star's face, some starlight filters through the planetary atmosphere. Different gases absorb different wavelengths, leaving characteristic fingerprints in the transmitted light. Future extremely large ground-based telescopes will push these capabilities even further. With mirrors spanning 30 or 40 meters, these instruments could potentially directly image planets around Alpha Centauri and analyze their reflected light for atmospheric composition. The biosignature gases that would indicate life include oxygen, methane, and other compounds in proportions that would be difficult to explain without biological processes. Earth's atmosphere contains oxygen only because photosynthetic organisms continuously produce it. Without life, oxygen would react with surface minerals and disappear. Finding oxygen in an exoplanet atmosphere would strongly suggest biological activity. Methane presents similar possibilities. On Earth, most atmospheric methane comes from biological sources. Detecting both oxygen and methane together would be particularly compelling. The detection of biosignatures in the Alpha Centauri system would constitute perhaps the most profound scientific discovery in human history. We would know with certainty that life exists beyond Earth. We would transform from wondering whether biology occurs elsewhere to knowing that it does. The philosophical implications would ripple through every aspect of human thought. Religious traditions, scientific paradigms, and cultural assumptions about human uniqueness would all face immediate revision. The universe would feel different, knowing that life has emerged at least twice in our cosmic neighborhood. And if life exists at the nearest star, the implications for life throughout the galaxy become staggering. 400 billion stars in the Milky Way alone. If even a tiny fraction host life-bearing worlds, the cosmos teems with biological experiments we have never imagined. The planets of Alpha Centauri represent humanity's best targets for answering the ancient question of whether we are alone. The worlds are close enough for detailed study. The systems are old enough for life to have evolved. The conditions, while challenging in some cases, do not definitively preclude habitability. Proxima b may be a radiation-scorched desert, or it may harbour life in deep oceans or subsurface refugia. Alpha Centauri A and B may host Earth-like worlds we have not yet detected, or their habitable zones may be empty. The only way to know for certain is to look more closely, and ultimately, to go there. The distances remain crushing. The technology remains inadequate, but scientists and engineers are already designing missions that might someday cross the void to our nearest stellar neighbours. The race to reach Alpha Centauri has begun, even as the destination seems impossibly far. 25 trillion miles, nearly 7,000 years at the fastest speeds humanity has ever achieved. an ocean of vacuum so vast that light itself requires over 4 years to cross it. Every calculation we have performed, every comparison we have drawn, every scale model we have constructed leads to the same crushing conclusion. Alpha Centauri is impossibly far away, and yet humanity refuses to accept impossibility. We have a peculiar habit of looking at barriers that seem absolute and asking how we might break through them anyway. The sound barrier was unbreakable until Chuck Yeager broke it. Heavier than air flight was impossible until the Wright brothers made it routine. The moon was unreachable until Neil Armstrong left footprints in its dust. Now, scientists and engineers are seriously designing missions to reach Alpha Centauri, not in millennia, not in centuries, in decades. Within a human lifetime, fast enough that the people who launch the mission might live to see the data return. The audacity of this ambition borders on absurdity. The distances involved exceed anything humanity has ever attempted by factors of thousands. The technologies required do not yet exist. The costs would strain the resources of entire nations. The probability of failure looms enormous over every proposed approach. But the work continues. Research teams around the world are tackling the engineering challenges. Funding organizations are committing resources. Theoretical physicists are examining what the laws of nature actually permit, rather than what conventional engineering suggests is practical. The race to reach our nearest stellar neighbor has begun. The finish line sits 25 trillion miles away, and no one knows if we can cross it. But we are trying anyway. On April 12th, 2016, Russian-Israeli billionaire Yuri Milner stood alongside legendary physicist Stephen Hawking and announced the most ambitious space exploration initiative in human history. Breakthrough Starshot would attempt what had never been seriously proposed before. The announcement electrified the scientific community. Milner committed an initial $100 million to research and development. Hawking lent his enormous credibility to the project, calling it the most exciting adventure ever to be undertaken by humanity. Mark Zuckerberg joined the board of directors, adding technological firepower from the digital revolution. The goal seemed almost delusional in its ambition. Breakthrough Starshot would send gram-scale spacecraft to Alpha Centauri at 20% of the speed of light. At that velocity, the journey would require approximately 20 years, rather than the millennia that conventional propulsion demands. 20 years. A spacecraft launched in 2040 could return data in 2064. The scientists proposing this mission could reasonably expect to live long enough to see the results. For the first time in history, interstellar exploration could fit within a human career. The core concept relies on light sails, ultra-thin reflective structures that gain momentum from photons striking their surfaces. The idea dates back decades, but Breakthrough Starshot proposed implementing it at scales never before attempted. Conventional spacecraft carry their fuel with them, burning propellant to accelerate and decelerate. This creates a fundamental problem for interstellar travel. The fuel needed to reach high velocities itself has mass. Accelerating that fuel requires more fuel. The mathematics spiral into impossibility as target speeds increase. Light sails sidestep this problem entirely. The spacecraft carries no fuel at all. Instead, a powerful laser array on Earth shines concentrated light at the sail surface. Photons carry momentum despite having no mass. When they bounce off the reflective sail, they transfer that momentum to the spacecraft. Continuous illumination produces continuous acceleration. The specifications Breakthrough Starshot proposed pushed every parameter to extreme limits. The laser array would need to generate approximately 100 gigawatts of power. This exceeds the entire electrical generating capacity of the United Kingdom focused into a single beam. The beam would need to maintain coherence across millions of kilometers as the spacecraft accelerates away from Earth. The sail surfaces would measure approximately 4 meters across, roughly the size of a small room. But they would need to weigh only grams. This requires materials thinner than any conventional structure. Reflective membranes, measured in nanometers rather than millimeters. The acceleration would reach approximately 60,000 times Earth's gravity, sustained for several minutes. The spacecraft would go from stationary to 20% of light speed in less time than it takes to watch a television episode. Any component unable to withstand this brutal acceleration would be destroyed instantly. The spacecraft themselves, called starships, would weigh only a few grams complete. They would need to carry cameras capable of photographing planets around Alpha Centauri, sensors to measure magnetic fields, radiation levels and particle densities, communications equipment to transmit data back to Earth across 4 light-years, power systems to operate all of this for the decades required for the journey and data return. Each of these requirements exceeds current technology by substantial margins. Packaging functional cameras, computers, transmitters, and power sources into gram-scale devices remains beyond present capabilities. The status of Breakthrough Starshot as of 2025 reveals a sobering reality about the gap between ambition and execution. The project has significantly stalled. The promised $100 million in funding never fully materialized in forms that supported actual hardware development. Researchers associated with the project report receiving less than 5% of program funding for their technical work. The grand announcements of 2016 have not translated into the rapid progress that initial enthusiasm suggested. This is not failure in the conventional sense. Research continues. Papers are published. Technical challenges are being addressed incrementally. In 2025, researchers from Brown University and TU Delft announced development of an ultra-thin light sail optimized using artificial intelligence. This sail measures only 200 nanometers thick and features billions of nanoscale holes that reduce mass while maintaining reflectivity. Such advances represent genuine progress toward the breakthrough Starshot vision. The gap between current capabilities and mission requirements remains enormous. The technical challenges facing breakthrough Starshot extend far beyond the initial acceleration phase. Every component of the mission concept faces obstacles that current engineering cannot solve. The sail material requirements alone seem nearly impossible. The sail must survive 60,000 gravities of acceleration without tearing. It must withstand intense heating from the laser illumination without melting or losing reflectivity. It must resist erosion from impacts with interstellar dust and gas over a 20-year journey. The interstellar medium is not perfectly empty. Trace amounts of hydrogen gas and microscopic dust particles permeate the space between stars. At low velocities, these particles pose no threat. At 20% of light speed, the kinetic energy of impact transforms each hydrogen atom into a tiny bullet. A spacecraft traveling at 60,000 kilometers per second would encounter approximately 10 hydrogen atoms per cubic centimeter of space traversed. Over 20 years and 4 light-years of travel, these impacts accumulate. Simulations suggest significant erosion of forward-facing surfaces. The delicate sail might not survive the journey intact. The proposed solution involves launching a fleet of approximately 1,000 spacecraft rather than a single probe. If 90% are destroyed by interstellar medium impacts, 100 would still arrive. If 99% fail, 10 would complete the journey. Redundancy compensates for the hazards that individual spacecraft cannot survive. But this multiplication increases costs, complexity, and the scale of the launch infrastructure by orders of magnitude. 1,000 spacecraft requires 1,000 successful accelerations, 1,000 sets of miniaturized instruments, 1,000 data streams to monitor and receive. Communication presents perhaps the most fundamental challenge. Signals from Alpha Centauri require over 4 years to reach Earth traveling at light speed. No real-time mission control is possible. Every decision the spacecraft makes must be programmed in advance or determined by autonomous systems operating without human guidance. Transmitting data back from gram-scale electronics across 4 light-years pushes against basic physics. radio signal strength decreases with the square of distance. A transmitter, powerful enough to be detected at 4 light-years, using gram-scale equipment and milliwatt power budgets, requires receiving antennas on Earth, measured in kilometers. The data rates would be agonizingly slow. Images that smartphones transmit in milliseconds might require hours or days to send from Alpha Centauri. The total data return from a successful mission might be measured in kilobytes rather than gigabytes. A few photographs, basic environmental readings, proof that the spacecraft arrived and functioned. Each technical challenge has proposed solutions. Each solution creates new challenges. The engineering pathway from current capabilities to functioning interstellar probes stretches through decades of development that may or may not succeed. While Breakthrough Starshot captures headlines with its audacious vision, a more modest mission approaches launch with concrete hardware and realistic goals. Ptolemy represents what we can actually accomplish in the near term, while dreaming of what we might achieve eventually. Ptolemy stands for Telescope for Orbit Locus, interferometric monitoring of our astronomical neighborhood. The name pays tribute to Alpha Centauri b, sometimes called Ptolemy in older star catalogues. The mission itself focuses on finding planets that might orbit both bright stars of the Alpha Centauri binary. Planned for launch in 2026, Ptolemy is not an interstellar mission. No spacecraft will travel to Alpha Centauri. Instead, a small space telescope will observe the system from Earth orbit, searching for the telltale gravitational signatures of unseen planets. The technical approach exploits a clever optical trick. Ptolemy uses a diffractive pupil lens that creates a distinctive flower-like interference pattern from observed starlight. This pattern is exquisitely sensitive to the precise positions of the stars being observed. If a planet orbits either Alpha Centauri A or B, its gravitational pull causes the star to wobble slightly. Ptolemy can detect these wobbles by measuring changes in the interference pattern over time. The telescope itself is surprisingly modest. A 12.5 centimeter aperture, smaller than many amateur instruments. But the specialized optics and space-based location above atmospheric distortion enable precision measurements impossible from the ground. The mission would operate for 3 years in a 550-kilometer sun-synchronous orbit, continuously monitoring the Alpha Centauri system. If Earth-mass planets exist in the habitable zones of either bright star, Ptolemy should detect them. The partnership supporting Ptolemy demonstrates how international collaboration enables space missions that no single organization could accomplish alone. Breakthrough Initiatives, the same organization behind Starshot, provides primary funding. The Australian government has contributed over $500,000 through various programs. The SmartSat Cooperative Research Centre coordinates Australian space industry participation. Technical collaborators include Spiral Blue for artificial intelligence and edge computing, Endurosat for satellite platform hardware, NASA's Jet Propulsion Laboratory for mission design expertise, and Sabre Astronautics for mission operations support. A precursor mission called Tollyboy launched in 2021 aboard the CUAVA-1 satellite to the International Space Station. This technology demonstrator tested components that would later fly on the full Ptolemy mission. Why does Ptolemy matter for the dream of interstellar travel? Because confirming habitable zone planets around Alpha Centauri A or B would transform the entire conversation about missions to our nearest neighbor. Proxima b orbits a violent flare star in conditions that challenge habitability assumptions. But Alpha Centauri A resembles our Sun almost exactly. Alpha Centauri b, while cooler, still provides relatively benign stellar conditions. Planets in the habitable zones of these stars would face none of the radiation challenges that plague Proxima b. Finding such worlds would provide compelling targets that justify the enormous investment interstellar missions require. The question would shift from whether we should try to reach Alpha Centauri to how quickly we can develop the technology to do so. Beyond Breakthrough Starshot and Ptolemy, other mission concepts have been proposed for reaching our nearest stellar neighbor. Each offers different trade-offs between technological feasibility, journey time, and practical implementation. Nuclear pulse propulsion represents one of the oldest serious interstellar concepts. Project Orion, studied extensively in the 1950s and 60s, proposed accelerating spacecraft by detonating nuclear explosives behind a massive pusher plate. Each explosion would vaporize propellant material, creating a plasma that slams into the pusher plate and accelerates the spacecraft. The physics actually works. Calculations suggested that Orion-style spacecraft could achieve several percent of light speed, reducing the Alpha Centauri journey to roughly 100 years. The concept requires no new physics, only engineering development of known principles. The problems are political rather than physical. Launching thousands of nuclear weapons into space, even for peaceful purposes, violates international treaties. The risk of catastrophic failure during atmospheric transit could scatter radioactive material across wide areas. Public opposition would be overwhelming, regardless of scientific merit. Nuclear pulse propulsion remains theoretically viable, but practically impossible in any foreseeable political environment. Antimatter propulsion offers the ultimate theoretical efficiency. When matter and antimatter meet, they annihilate completely, converting all mass to energy according to Einstein's famous equation. No other reaction extracts so much energy from so little mass. A spacecraft carrying antimatter fuel and reacting it with normal matter in a controlled fashion could achieve extraordinary performance. Journey times measured in decades become plausible. The physics is spectacular. The reality is crushing. Humanity currently produces antimatter in quantities measured in nanograms per year at facilities like CERN. The cost per gram exceeds trillions of dollars. Producing the quantities needed for interstellar propulsion, measured in tons, would require centuries at current production rates and expenditures exceeding global economic output. Antimatter propulsion remains pure science fiction for any foreseeable future. NASA examined an interstellar probe concept around 2017 that proposed launching a mission on the 100th anniversary of Apollo 11 in 2069. This probe would use solar sail propulsion combined with high-energy laser acceleration to achieve approximately 10% of light speed. At that velocity, the spacecraft would arrive at Alpha Centauri in 2113, 44 years after launch. Scientists working on the mission in 2069 could reasonably expect to see the data return before they died. The concept remains unfunded. NASA's budget priorities focus on near-term objectives like lunar return and Mars exploration. Interstellar missions represent generational investments that current political and funding structures do not support. Slowboat missions accept much longer journey times in exchange for near-term technological feasibility. Advanced ion engines could potentially achieve velocities of several hundred kilometers per second, far faster than any current spacecraft, but still minuscule compared to light speed. At such velocities, reaching Alpha Centauri would require approximately 10,000 years. The spacecraft would eventually arrive, but no one associated with the mission would live to see it. Their descendants for hundreds of generations would need to maintain interest and tracking capability. Such missions raise philosophical questions that science alone cannot answer. Who funds 10,000-year projects? What institutions survive long enough to receive the data? Does the information remain valuable after so many millennia? Cathedral building offers the only historical parallel. Medieval Europeans invested generations of labour into structures they knew they would never see completed. The motivations were religious rather than scientific, but the commitment to projects transcending individual lifetimes demonstrates that such endeavours are possible. Whether humanity could summon similar commitment for interstellar exploration remains unknown. The stalled progress of Breakthrough Starshot illuminates a fundamental challenge facing any interstellar mission. These projects require sustained commitment across timescales that human institutions struggle to maintain. Political systems operate on cycles measured in years. Elected officials focus on achievements they can claim before the next election. Funding decisions reflect immediate priorities rather than generational investments. A president who commits billions to an interstellar mission will be long out of office before any results arrive. Economic systems similarly prioritize near-term returns. Investors expect profits within years, not centuries. Corporate planning horizons rarely extend beyond a decade. Scientific funding faces its own constraints. Researchers build careers on publications and results. A scientist who devotes their career to a mission that produces data after they die receives no professional benefit from the work. Grant agencies favor projects that will yield results within the grant period, typically 3 to 5 years. The unique challenges of interstellar missions compound these difficulties. The technology required does not yet exist. Development timelines stretch across decades with uncertain outcomes. Costs exceed any single nation's science budget. Success is not guaranteed, regardless of investment. Every other space mission in history, even the most ambitious, operated within comprehensible timescales. Apollo reached the Moon in 8 years of focused effort. The Voyager spacecraft continue operating decades after launch, but they were designed, built, and launched within normal program cycles. Even the James Webb Space Telescope, plagued by delays and cost overruns, eventually launched and produced results. Interstellar missions occupy a different category entirely. They require creating technologies that do not exist, sustaining funding across generations, maintaining institutional commitment through leadership changes and political upheavals, and accepting that success may come decades after the effort began. Medieval cathedrals provide the only real historical precedent. Chartres Cathedral took over 50 years to build. Notre Dame de Paris required nearly 2 centuries from foundation to completion. The workers who laid the first stones knew they would never see the finished structure. Those cathedrals were built because religious faith provided motivation that transcended individual lifetimes. The builders believed their work served eternal purposes that justified sacrifices they would never personally see rewarded. Does humanity possess equivalent motivation for interstellar exploration? Can secular goals command the commitment that religion once inspired? The question remains open, and the answer will determine whether we ever reach the stars. Despite the challenges, the potential rewards of reaching Alpha Centauri justify continued effort. Success would transform human civilization in ways that ripple through every aspect of our existence. The scientific revolution would be immediate and profound. For the first time, humanity would directly observe another stellar system. Every previous astronomical observation has been conducted from within our solar system. Even the most powerful telescopes see distant objects as points of light or fuzzy blobs. A spacecraft at Alpha Centauri could photograph planets, measure atmospheric compositions, detect magnetic fields, and characterize environments in ways impossible from 4 light-years away. The habitability questions surrounding Proxima b would be resolved definitively. Does the planet retain an atmosphere despite billions of years of flare bombardment? Does liquid water exist on its surface or beneath it? Are there any signatures that might indicate biological activity? If Alpha Centauri A or B hosts planets, as Ptolemy may discover, those worlds could be imaged and characterized as well. The binary star environment might produce planetary conditions unlike anything in our solar system. Understanding how planets form and evolve in binary systems would fill major gaps in astronomical knowledge. Our theories of planetary formation derive almost entirely from studying our own singular solar system. Alpha Centauri offers a natural laboratory for testing those theories against radically different configurations. The technological transformation required to reach Alpha Centauri would spawn innovations applicable across countless industries. Miniaturization advances needed for gram-scale spacecraft would revolutionize electronics, medical devices, and robotics. Laser technology improvements would enhance communications, manufacturing, and energy systems. Autonomous systems, capable of operating for decades without human intervention, would transform automation everywhere. History demonstrates that ambitious space programs produce technological spin-offs far exceeding their direct objectives. The Apollo program generated advances in computing, materials, science, telecommunications, and medical technology that continue benefiting society decades later. An interstellar program would do the same, but amplified by the even greater technical demands involved. The civilizational milestone would perhaps matter most of all. Successfully sending spacecraft to another star would transform humanity from a species confined to a single stellar system into an interstellar civilization. We would no longer be bound to the small region of space where we evolved. The psychological impact would ripple through human self-understanding. Every previous human achievement, no matter how impressive, occurred within our solar system. Interstellar travel breaks that boundary. It demonstrates that the galaxy is accessible, even if difficult. It proves that the vast distances between stars, while enormous, are not infinite barriers. Alpha Centauri would become a gateway to the cosmos. The technical capabilities developed for this first mission would apply to subsequent targets. The lessons learned would accelerate future efforts. Each successful interstellar mission would make the next one easier. The journey of 1,000 light-years begins with a single 4 light-year step. Even if humanity successfully reaches Alpha Centauri, a sobering reality awaits. Our nearest neighbour represents the minimum possible interstellar distance. The galaxy beyond stretches vastly larger, and most of it will remain forever inaccessible regardless of technological progress. 400 billion stars populate the Milky Way galaxy. They are scattered across a disk, 100,000 light-years in diameter. Alpha Centauri sits 4.37 light-years away. The galactic centre lies 26,000 light-years distant. The far side of the galaxy stretches 75,000 light-years beyond our position. If reaching our nearest neighbour requires revolutionary technology and decades of travel time, what about stars 100 light-years away? 1,000? 10,000? The mathematics scale brutally. A mission travelling at 20% of light speed, the ambitious target of breakthrough starshot, would require 500 years to reach a star 100 light-years distant. 1,000 light-years would demand 5 millennia. The galactic centre would require 130,000 years. No conceivable technology circumvents this fundamental barrier. The speed of light imposes an absolute limit that physics appears to forbid exceeding. Wormholes, warp drives, and other science fiction concepts remain entirely theoretical, with no experimental evidence suggesting they are physically possible. Even if revolutionary physics somehow permits faster-than-light travel, the energy requirements for any plausible approach exceed the output of entire stars. The practical barriers stack upon the theoretical ones, creating walls that may prove permanently insurmountable. This reality explains the silence that pervades the cosmos. The Fermi paradox asks why, given the vast number of stars and the great age of the galaxy, we have detected no evidence of other civilizations. The distances provide an answer. If intelligent species arise on planets throughout the galaxy, each one faces the same crushing geometry we face. 4 light-years to the nearest star, hundreds of light-years to significant stellar populations, tens of thousands of light-years to span the galaxy. Even civilizations, millions of years more advanced than humanity, cannot overcome the fundamental physics of space-time. They may have spread to nearby stars over millions of years of patient expansion, but the galaxy is vast, and even light-speed travel requires 100,000 years to cross it. Perhaps every intelligent species that evolves eventually confronts this same wall. Some worlds can be reached with sufficient effort. Most cannot. The galaxy remains an archipelago of isolated islands, each separated from the others by oceans too wide to cross. Alpha Centauri represents the first island beyond our own. Alpha Centauri embodies the central paradox of cosmic existence. Our nearest stellar neighbour sits close enough that we have mapped it in extraordinary detail. We know the masses of its 3 stars. We have confirmed planets orbit at least one of them. We have identified possibly habitable worlds within the system. Yet 25 trillion miles of empty vacuum separate us from this intimately known neighbour. The distances mock our knowledge. We can describe Alpha Centauri in precise detail while being utterly incapable of visiting it with current technology. This paradox extends throughout the cosmos. The universe reveals itself generously to our telescopes and instruments. We observe galaxies billions of light-years distant. We detect radiation from the first moments after the Big Bang. We map cosmic structures spanning hundreds of millions of light-years, and we cannot visit any of it. The cosmos permits observation, while forbidding exploration. We are allowed to look, but not to touch. Alpha Centauri represents humanity's test case. If we can develop the technology to cross 4 light-years, the next target becomes possible. And the next. Incremental expansion might eventually carry human presence or human machines across significant portions of the galaxy. If we cannot, if the barriers prove permanently insurmountable, then we remain forever confined to our single stellar system. The Sun and its planets become not our starting point, but our entire universe. Everything beyond remains eternally out of reach. The importance of continuing to try transcends any specific mission outcome. The effort itself demonstrates something profound about human nature. We evolved on a small planet, orbiting an ordinary star in an unremarkable corner of an average galaxy. Nothing in our evolutionary history prepared us for contemplating interstellar travel. Yet here we are, designing light sails and laser arrays, calculating trajectory corrections and communication protocols, dreaming of spacecraft that might someday cross the void to other stars. The ambition itself matters regardless of whether it succeeds. 4.37 light-years, 25 trillion miles, 3 stars locked in gravitational embrace across timescales that dwarf human existence. Worlds that might harbour conditions for life, bathed in radiation from a violent red dwarf or warmed by the gentle light of sun-like stars. Journey times measured in human lifetimes if revolutionary technology succeeds. Journey times measured in geological epochs if it does not. The paradox of proximity that remains impossibly distant. The knowledge that tantalizes while remaining beyond our grasp. The frontier that represents either humanity's first step toward the stars or the boundary we may never cross. Alpha Centauri is all of these things simultaneously. Our nearest neighbour, our greatest challenge, our test of whether the cosmos can ever be more than something we observe from afar. The true scale of Alpha Centauri encompasses everything we have explored. The crushing distances that reduce our fastest spacecraft to crawling insignificance. The 3-star architecture that has danced through space for billions of years. The planets that orbit in conditions we are only beginning to understand. The missions that might someday carry human technology across the interstellar void. Understanding this scale transforms how we see ourselves. We are one species on one planet, orbiting one star among 400 billion in a galaxy, among 2 trillion scattered throughout the observable universe. Our nearest stellar neighbour already lies beyond our reach. The vast majority of cosmic existence will remain forever inaccessible regardless of what technologies we develop. And yet, humanity continues to reach. Scientists design missions. Engineers solve problems. Visionaries commit resources. The dream persists despite the obstacles. Alpha Centauri waits. It has waited for nearly 5 billion years. It will continue waiting for billions more. The question is whether humanity will find a way to answer its silent invitation. The true scale of our nearest neighbour reveals both our cosmic insignificance and our remarkable ambition. We are small beyond measure against the backdrop of the universe, but we are the part of the universe that is trying to understand itself, trying to explore itself, trying to transcend the boundaries that physics and distance impose. That effort, regardless of its ultimate success, represents something precious. Among all the matter and energy scattered across the cosmos, among all the stars and planets and galaxies stretching to the edge of observation, we are the part that wonders. We are the part that reaches. Alpha Centauri represents where that reaching might someday take us. The first step on a journey we can barely imagine, the nearest destination in a cosmos that stretches incomprehensibly beyond it. 4 light years to the first star, the rest of the universe beyond.